to study mass transport in the environment like ocean currents. So, well, the topic of radionuclide releases have lately received much more attention and also gained some new relevance because of the new European taxonomy law, which labels nuclear power as a green and a sustainable energy, and of course also unfortunately due to this really dangerous situation we are facing due to the war in Ukraine, which of course troubles me quite a lot. But now coming back to the label of sustainability for nuclear power, I have to mention that I don't feel like an expert to really comment on whether this is reasonable or not, since I am not an expert on the nuclear fuel cycle or nuclear power production in general. But if I already draw your attention to this lower picture here, which shows you the release of a radionuclide or radioactivity after the Fukushima accident, then of course one might question already whether this is a really sustainable source of energy production. Yes, so in general, what my talk is today is about actually dealing with the legacy of the nuclear age in general, which is of course also the nuclear weapons testing predominantly, which have introduced quite a number of new elements and of course radioisotopes and into the environment, which are actually not naturally occurring on significant levels. And so also you have to be aware of that these radionuclides I'm dealing with, they have a very long half-life. That means that they will stay in our environment for over hundreds and thousands of years and will take part into the redistribution processes on the globe, which of course needs some kind of monitoring already now on the low environmental levels, what we have fortunately still until now. And also on the other hand side, they provide a possibility to use them as a tracer for this ocean currents, which was mentioned before. So you see that my research usually also always have these two sides of a coin. So monitoring on the one hand side to get an idea about the redistribution and also to assess some kind of hazard from these isotopes, and on the other hand side to use them as a tracer for environmental transport processes. Having a short look onto the overview of my talk, of course, I first would like to introduce you to, in general, radioisotopes and the respective emission sources. And since this lecture series in this semester is on the sustainability, I also would like to discuss these different emission sources in a bit more detail. Afterwards, of course, I also want to discuss the detection methods, which depend on the activity and therefore also the half-life of the radionuclides we are talking about. And of course, certainly I will focus on the method we are using here at the Vienna Environmental Research Accelerator, which is Accelerator Mass Spectrometry. I will proceed with a discussion of how we could use or how we are using these radioisotopes as environmental tracers and give some examples. And a topic which has become quite important and the public is really interested into that is using defining, first of all, some kind of marker for the new geological age of the Anthropocene and how these isotopes could play a role as a so-called golden spike to define the basis of the new geological age. And at the very end, if there's some time left, I would also look to give an outlook and where our research is going to. And certainly at the moment, we are much focusing our research in the physics part of my work on the ion laser interaction mass spectrometry. And of course, I would like to give a short introduction into that field. first of all, to get us all onto the same page, let's say, I first would like to remind you a little bit of what are actually isotopes and how does that depend on the structure of the atom. So basically, if we start with the periodic table, which is presented on that slide, then you see that all these elements are placed in a certain position according to their chemical properties, which of course depend on their atomic shell, on the electrons in the atomic shell, and hence, since the atom is to be neutral out from outside, then on the number of protons you have in the nucleus. Now I picked a certain group of these elements which will become very important in this follow-up discussion, which is the group of the so-called actinides, which is marked here actually only by 2 stars because it's a huge number of elements actually. And of course, it's important for us because uranium is part of this group. And as you all know, uranium is the fuel for nuclear power production and also usually is used in nuclear weapons. And we can build up all these higher actinides by adding neutrons to the nucleus, which have no charge at all. And then we can produce by some physical transformation, and which is actually then the radioactive decay, produce new elements out of it, which actually do not occur in nature. But if you want to look, have a closer look into which of those isotopes of these nuclides of these elements are important for my research, then we have to change from the periodic table of elements to the nuclide chart, which is preferred actually by the physicists, which shows you the different elements in the different lines. So that actually corresponds to the periodic table we have seen before. And as I told you before, these elements, they differ in the number of protons in the nucleus. And what we have now on the x-axis is the number of neutrons. So I can have different so-called isotopes of the same element with a different number of neutrons. And of course, the 2 which are most important for nuclear power production is mainly uranium-235, which can be fissioned to produce the energy out of this process. But you see that actually the abundance is very low, and the major part of uranium, what we find in nature, is uranium-238, and you see that just the mass number is differing, which depends on the number of neutrons. And now starting from those 2 isotopes of uranium, we can build up these higher isotopes of different elements of neptunium, plutonium, and americium. And I've already marked in blue those which are especially interesting for my research. And this is because of these very long half-lives you see here, like of at least thousands of years, that makes them therefore have a rather low radioactivity, but they will stay in our environment for really, really long time scales, and we have to care about what happens to them in the environment. And now, why are we actually now also interested in those radioisotopes for tracing? This I want to explain you with these a little bit bold, but really illustrative pictures here. Like showing you that if you put some little shovel of sand, a little amount of sand in an environment where you would not expect it to be there, like here on the lawn of this grass, then it is really obvious by the eye that there's some change happening here in the system. However, if you put this into a desert where you already have a lot of sand, you have to have a very close look to see this extra amount of sand you have placed there. And actually, it's very much the same for our isotopes. If you consider rare isotopes or like the stable ones, which are all around, then if there's some transport of stable isotopes which make up our overall environment, then you would not recognize, or it's hard to recognize. That means you have to make really precise measurements of the concentration to see that there has been some changes going on. However, if there is a isotope, a rare isotope, which is not expected to be there, like for example, the radioisotopes, which are actually not occurring in nature, then it's quite obvious that there has been some transport of this isotope to that place we are looking at. And of course, in addition, in some few cases, also the radioactive decay helps to provide some additional time information about the different processes which are involved, because showing here on this little picture showing that the radioactive decay is of course an exponential decay, so that after the half-life you have only half of the amount you were starting with, and this gives you the time information. However, before using those radioisotopes for monitoring these changes in our environment, we really have to get a deep understanding of their behavior and how they are transported in the environment, because when you want to use them, you have to make sure that they really behave like the medium you're actually tracing. So that means they are really transported, for example, with the water masses. And of course, naturally, also this knowledge is very important to prevent the spread of these radionuclides in case of an accidental release of higher concentrations of these isotopes, which might pose a risk to the wildlife or even maybe to mankind, like we have been facing also in the reactor accidents, of course. Actually, to show you that this is not a very trivial question, I placed here a publication, which is already some time ago, but it shows you that the overall transport behavior, what we call then in this context, the migration behavior, for example, of plutonium, is very difficult to define, because it very much depends on the environmental conditions you're facing. And in that case, the authors, so Kersting et al., they found that actually plutonium, which was supposed to be a rather immobile element, was found several kilometers away from the testing site in Nevada. And this was because it was just attached to some colloids, and the colloids were transported. And this example should show you that it is really important that we take into account all these environmental conditions when we're studying this so-called migration behavior, and not only the elemental or let's say the chemical characteristics of the element itself. And this means that we have to study the distribution and the spread of these elements already, what we have already in the environment, and to take all these different, the different parameters into account. And of course, this understanding is not only important for the tracer studies, so for the environmental sciences, but also, of course, if you're dealing with nuclear waste management, if you're thinking about a final repository. And as I already said, like for radioecology, that means in cases of accidents. What is the basic problem? Just to give you some insight into that, why it's that complicated, when especially looking into the elemental group of the actinides, which I have shown already before, then if you only look at the chemical characteristics, then you could define the oxidation state, which is already quite complicated to do for the actinides, because they can adopt a different oxidation state depending on the redox potential you have in the environment. But if you're going for like oxic conditions, then you can basically split them into two groups, like americium plutonium, which are supposed to be rather particle reactive. That means that they get absorbed onto particles or even surfaces, would mean that they are immobilized. And the second group here is the group of neptunium and uranium. They are in higher oxidation states, but in general then in the water, they are well soluble. That means that makes them very good oceanographic tracers or water tracers, because they are really transported in the water with the water masses. But of course, this also makes them problematic for nuclear waste storage if you have a water breakthrough in your final repository. But I have already shown you before, if you're facing or if you're studying this, the behavior in real environmental system is not that easy. And as I said before, you would expect then that plutonium and uranium would be stationary, because if you look at this little picture here on the bottom, which is actually provided by the test repository at the Grimsel site in Switzerland, you can see that these particles or these elements can get attached to colloids, and the colloids are then transported over some distances. And of course, you can also face some remobilization of nuclides which were actually attached to the walls of your water channel, for example. And you can have a lot of different components in the environment which can lead to complexation. That means that you form like bigger compounds which are then water soluble. And actually, this also helps us for uranium when using it as an oceanographic tracer, because uranium likes to form carbonate complexes, which makes it even more soluble. And a totally different question is, what actually are these elements doing when you are having reducing condition? That means low redox potential in terms like low pH value or so that means that then the oxidation states, the preferred ones, what I have told you before, they might change completely. So let's have a look now actually on the emission sources of the radionuclides, which have caused to the release of radionuclides into the environment. And of course, and then on the global scale, the dominating source definitely are the atmospheric nuclear weapons tests, which were conducted in the 50s and 60s, mainly by the US and the Soviet Union, with a maximum deposition in 1963. But we also have some more local impacts, which may even in this local area may even be higher from the concentrations point of view, like the reprocessing plants from the nuclear fuel cycle, especially those in Europe like La Hague and Sellafield, and I will show you some data on that later on. And of course, the major reactor accidents, like especially Chernobyl and Fukushima accident. And there are also some accidents just with nuclear materials where, for example, airplanes crashed carrying nuclear weapons, or we also had some burn up of satellites which were fueled, which used some batteries fueled with like plutonium or uranium. I will not go into that detail with these sources, because actually this has been remediated, these areas, and they are very much localized. And do not add so much to the overall global budget of radionuclides. Looking now a little bit more detail on the nuclear weapons emissions, then you see that we can have here, we see the number of tests over the years, and you see that it is peaking, like what I said before, in the 60s. But it is even more important to look on the overall explosive yield, which is somehow correlated to the emission of radionuclides, because if you had a higher explosive power, then usually you also had a higher release. And especially if you look under that little scheme, which was produced by Libby, who received the Nobel Prize for the radiocarbon dating method, you can also find some differences in the type of weapons and how the fallout is produced. And you will find that especially the large H bombs, the so-called fusion bombs, they have produced this global fallout, which was spread over the whole globe. And actually, most of it was produced then here in the 60s, which was predominantly caused by the Soviet Union. Having just a short look onto the releases in this weapon test, it might be also interesting for you to see that you can find all this data listed, for example, by UNSCEAR or also by the IAEA or WHO, they have all these reports where you can find the data. But of course, it only refers mainly to those which really introduce some radioactivity in the environment, because this is, of course, most important for the protection of the environment so far. And these ones which we are most interested in, those with the long half-lives, they actually have a lower radioactivity release. That's just because, of course, because they have this longer half-life, and you see that they actually only add like 6 petabecquerels, and this means this is 10 to the 15. This is already huge. But then calculating the mass, of course, then you will see that the masses are really, threatening, let's say. So there were a huge number released of these isotopes, but of course it was spread over the whole globe, so that in general, from the nuclear weapons test, the overall concentrations are radiologically not relevant, only on the test site itself, of course. And especially then you see that plutonium from this long-lived radionuclides is the dominating one, followed by the neptunium and the uranium. And this is actually data which was provided also by our measurements using the Accelerator Mass Spectrometry, which already shows you that the overall concentrations in the environment are very, very low. And we also have to apply this ultra trace methods for the detection. Now, if we proceed into the nuclear fuel reprocessing, I just want to give you a little bit of an insight what is actually the aim and what is happening there. And you see then on this little scheme that if we start with enriched uranium, which is needed for the nuclear fission, so that we can really produce nuclear power out of it, then you see that when it is what we call burned in the nuclear reactor, the overall amount or percentage of uranium-235, of course, is decreased, as well as also uranium-238, and you build up the other actinides, what I told you before, and of course also some fission products. But you see that the largest fraction of uranium is still there, and that means that actually this one-through cycle where you only use this fuel, the uranium fuel, just once, has a rather low efficiency. And actually you could still use this uranium in a different type of reactor, and especially also the plutonium again. So the idea of the reprocessing is that you separate the fission products, especially, and then of course, especially uranium and plutonium from the rest of the high radioactivity products which are produced in addition. Not going into further detail here, I just want to show you, give an idea how this is done. So actually it's kind of it is a chemical separation, what you have to do here. And in principle for the most relevant process, which separates uranium and plutonium from the rest, which is called the Purex process, your fuel elements have to be dissolved in nitric acid, in concentrated nitric acid, and it is mixed with an organic solvent. And then you will have a transition of uranium plutonium into the organic solvent, and the rest just stays in the nitric acid, and then you can separate those two. And this one, of course, then you have to extract uranium plutonium from this organic solvent in the end. And this, and finally then, is then the high level waste, which means that it has a high radioactivity. It's still producing quite a lot of heat. And so you have to get it into a stable form. And what is done actually then is that it is vitrified, and finally it looks a little bit like this, which is then supposed to be stored in the final repositories. But it means that during this chemical processing, you also would emit a certain type of elements, especially those which are gaseous, like the noble gases, or which are volatile, like iodine. And that means that during this processes, these reprocessing field, the reprocessing plants, especially Sellafield and La Hague, as been mentioned before, they emitted quite a number of, quite some amount of isotopes and radionuclides into the environment. And this is shown here, and actually you could also find it on the web page of Areva, for example, for La Hague. But when I wanted to look up some more recent values, I just learned that there's no Areva anymore, and it is now a new company, and there it is not that easy to find these values. But luckily, also our community is providing a lot of data on these emissions and on how they, the concentrations in the environment, and we could reproduce also the emissions. And you see this here, for example, for this radionuclide cesium-137, rather complete history of the emissions for the two, especially for Sellafield in that form, and then also La Hague, but La Hague is much lower. And you see that there was quite some drop in the La Hague's emissions in the 80s. So when the limitations were decreased quite a lot. So that you have for the protection of the environment, of course. And if we now look at the long-lived radioisotopes, then also there has been a lot done by the community of Accelerator Mass Spectrometry, also, for example, our colleagues in Spain. And then you see that especially for iodine, La Hague is a dominating emitter, which even emitted in total more than the global fallout here in yellow. And also Sellafield released more iodine than the nuclear weapons testing. So iodine is really a problem when talking about releases from reprocessing plants. Is different for uranium-236 and neptunium-237, but still you see also here Sellafield is a major emitter of neptunium and also uranium-236. And you see that there's some kind of pattern, especially also for technetium-99, which I'm very much interested in. Which it has to do with the operation of the reprocessing plants. And this is what we call a source term, and also the composition of these isotopes is what we call an isotope signature, because you would now distinguish the different emission sources from reprocessing plants and the global fallout from the nuclear weapons testing, and especially here also for technetium. You have a strong signal from Sellafield because there were hardly any emissions from La Hague. I don't want to talk too much about this emission from the reactor accidents because, actually, I just want to compare this two a little bit to give you some idea on how to put that into context. So if you first look to the more volatile and more soluble elements like the noble gases, and again, like iodine and cesium, what I told you before is rather mobile, then you see that the emissions of Fukushima and Chernobyl are roughly in the same order of magnitude. But if you look to the refractory elements, and especially the actinides, which I'm most interested in, then you have much higher emissions for the Chernobyl accident because, as I told you before, they are attached to the fuel particles. They are inside of the fuel particles. And this is a different, it was a different type of accident, actually, what happened in Chernobyl, where the whole reactor core exploded, whereas in Fukushima you had the hydrogen explosions, where mainly those volatile radionuclides were emitted. And we can see that also in this radionuclide signatures, what I told you before. And now looking onto a map of the plutonium emissions from the Chernobyl accident, which is where the Pripyat is located right here, then you see that also the emission of plutonium attached or included into the fuel particles is locally restricted. So that means on a global scale, we do not find so much plutonium released from this accident, and is more a problem of the area directly neighboring the nuclear power plant. Now, Coming to the detection of these long-lived radionuclides, of course, if you are in the restricted area, like around Chernobyl and Fukushima, then of course you can do just a simple activity measurement, because unfortunately there the concentrations are sufficiently high that you can just detect the nuclear decay. For example, in this case of plutonium, we have an emission of an alpha particle, which could be in principle detected. However, as I told you before, fortunately, if you go at the larger distances to these emission sites, then the concentrations are still very, very low. They are really on the trace amount or trace level. So if you look, for example, in the Pacific Ocean, where we actually had the testing from the US, then the concentrations of plutonium in 1 liter of ocean water is just 10 to the 7 atoms. I usually compare that it's like measuring a sugar cube in Lake Constance. Yeah, finding this sugar cube in Lake Constance, just to give you an idea. So concentration is really, really low. And with this little calculation here, without going into detail, I just want to show you that just measuring the activity will not work to really quantify the plutonium concentrations in the general environment. Because the decay rate is just too low. You would end up for this amount of plutonium in like 0.03 plutonium decays per hour. If you want to have some kind of precision onto your result of the concentration, let's say 3%, this would mean that you have to measure like 30,000 hours or use really huge amounts of sample material. So that of course doesn't work. So that's why we prefer atom counting. And if we go to the method of accelerator mass spectrometry, then, and especially our setup here, the Vienna Environmental Research Accelerator VERA, then we can measure around 30,000 plutonium atoms in just 1 hour. How does it work? Without going into much detail, in principle, this is a general setup of AMS, so Accelerator Mass Spectrometry, which actually is usually given by a mass spectrometer, actually 2 mass spectrometers here and there, which is linked by a particle accelerator, so-called tandem accelerator. Like all mass spectrometric techniques, we need to have charged particles. That means we have to use some kind of ion source, which in our case has to produce negative ions. That means that to the neutral atom, we just have to add another electron so that we can manipulate these ions in electrostatic and magnetic fields just to filter out a certain mass and to find the mass we are looking for in this huge background of other isotopes which are in our sample. And now the problem usual mass spectrometry is facing is that we have a huge background which is of orders of magnitude higher of molecules of the same mass. If you look for plutonium-239, for example, we have to face several orders of magnitude higher amounts of uranium-238 hydride, which could not be separated by a usual mass spectrometer. This is the reason why we are now using this type kind of accelerator, where we have, after a first acceleration stage, we have in the middle, we have a short pathway which is filled with a dilute gas, where due to the interactions, we just break up the molecular bindings and have a second acceleration stage. And then afterwards, we are now able to filter again according to the mass, because now we have really plutonium-239 or uranium-238 and the hydride or the hydrogen. And in the second mass separation stage, we then can distinguish between the 2 types, or the molecular background and the isotope of interest. Of course, in the end, we still have to use some kind of particle detector where we measure the remaining particles after several filtering steps according to their energy, which gives us information to the mass. If we now look to the setup of VERA, it looks a little bit more complicated, but in general, we still see the first mass spectrometer and the second one linked by a tandem accelerator, which has an accelerating voltage of 3 million volts. In general, you see here our sample wheel, which is placed into an ion source accepting 40 samples. And the second beamline is now our new setup, which I might touch at the very end of my talk. So basically, that means we are starting with some molecules which are negatively charged, and they are then broken up in the accelerator, and then afterwards we have positively charged. And the special feature of VERA is the second analyzing magnet, or magnet on the high energy side here, which allowed us to measure very, very low concentrations and actually allowed us to measure this new isotope of uranium-233 in the first place. And again, I want to point out to the very low detection limits, which gives you an idea about the environmental concentrations we are analyzing. Just a picture of the setup so that you get an idea with my colleagues Peter Steyer and Robin Golzer. And here's the accelerator, and actually this is the high energy mass spectrometer. So just to have an idea about the size, and this is the second magnet, and the ion source will be somewhere behind that wall. Also, I would like to shortly to address the sample preparation so that you know what kind of material we need actually for the measurement. I have shown you the sample wheel, and at the end we need some few micrograms of solid material. So if we start with some kind of sediments, for example, we first have to do some leaching to extract our isotopes or radionuclides. And then we do some column separation to obtain the uranium, plutonium, neptunium fraction, and the americium fraction. We then do some kind of co-precipitation with iron, which is calcined then at high temperatures, so that we obtain something like a few milligrams of iron oxide, which is now known as rust actually. And this is then pressed into our sample holders. This takes around about 5 days from the initial sample to the final AMS sample. Okay, that's which brings me to some selected applications of this method. And of course, I would basically focus now on the applications of oceanography, where I actually would like to focus on the isotope of uranium-236. In the first place, which I already told you is well suited to do so because it's transported with the water masses as a carbonate complex. And to show you this potential of uranium-236, I've selected the studies here by Nomura et al., who studied the concentration of uranium-236 in time-resolved coral cores. And this is a really nice archive because similar to tree rings, we have some annual bands, so you get some nice time information. And if we look now at the first coral core collected here in the main flow direction from the Pacific Proving Grounds, where you had this large atmospheric testing, we can really reserve different testing series from the US, which were conducted there. And if you look into the smaller branch, then you see that this is a bit washed out already, much lower already in concentration. So the signal in general is much lower. And this tiny signal here is actually now the signal from the global nuclear weapons fallout, which was analyzed in corals from the Caribbean Ocean, where you see the bomb peak, which refers to, or which corresponds to the maximum deposition in 1963. And from the decrease here after the maximum deposition, the authors here, Winkler et al., were able to calculate the transit time of the water masses from the intertropical conversion zone to this place here where the samples were collected. So this is already some important information on the water transport in this region. What I told you before is also that you could do so also in the North Atlantic Ocean, which is of course very important now in the respect of climate change, where we know that the composition will change, and that the currents will somehow change, especially the Gulf Stream will weaken within time. So we could use, or the colleagues here from the ETH search use the signals from Sellafield here and La Hague to reconstruct the ocean currents, which you see here. And you can see then on the lower pictures for iodine and uranium-236, the reconstructed emissions from the two reprocessing plants. And as I told you before, iodine-129 is mainly emitted from La Hague reprocessing plant, and you see that the major or highest concentration you find along the coast of Germany, which then is transported to the Norwegian coast, whereas the signal of uranium-236, which is also emitted from Sellafield in reprocessing plant, is transported around the Scotland coast and then here mixes before it joins the signal from La Hague and is also transported northwards into the Arctic Ocean. And of course, some signal is also transported into the Baltic Sea. I'm more interested into the region of the Pacific Ocean to find some signals there in order to get some information on this very important mixing region of the Indonesian through flow between the Pacific and the Indian Ocean, because it's very important for the energy budget in these two regions. And we have some samples already collected, and some of them already measured from the geocaresis cruise. And we will follow up also with some coral cores in this region. Here we first have to identify possible radionuclide markers, for example, as of course also from the Fukushima accident. In general, I will keep that very short, as also regarding the time already, we could maybe discuss that a bit later in discussion if you're interested. In principle, we can use the plutonium built up in these two sources, which differs because of the nuclear characteristics from which we face or what we have in nuclear power plants and what we have in nuclear weapons testing. And then we see that the buildup happens differently in the two emission sources, and we can use the ratio to identify. Most importantly, to distinguish Fukushima accident from the nuclear weapons testing is the time actually when it happened. Because here we have the rather short-lived plutonium-241 with only 14 years half-life, which serves as something like what we call a nuclear clock. This simply means that actually most of the plutonium-241 emitted by the nuclear weapons testing has already decayed, and whereas we have a fresh signal from the accident. And in fact, this was used to determine some emission of plutonium also from the Fukushima accident in the directly neighborhood, or that it means the restricting zone around the power plant, because the ratios of plutonium-241 to plutonium-239 were a little bit increased, and which already indicates a release. What I did in my PhD thesis was to look onto the liquid releases into the Pacific Ocean. And the good news here is that we did not find some increase of this ratio. And this was also confirmed in many other studies in the past. However, in this rather narrow region close to the power plant, you will find in the sediments a little bit increased signatures, but that does not mean that you really have some additional amounts of plutonium added into the environment. It's just that you see some variation. The fact that you find it in the sediment, that already shows you this particle reactive behavior. That means that plutonium actually is not a good tracer for water masses, and therefore we were actually looking for an isotopic ratio for uranium, which we find is a suitable tracer. And we were expecting to find a difference in the uranium-233 to uranium-236 ratio, depending on if it was produced in nuclear power plants. That means then also finally in the emissions from nuclear reprocessing compared to global fallout, just also again about just looking at the nuclear characteristics of the two sources. And in fact, we also really found a difference when looking at different archives, which were either affected by nuclear reprocessing, which would be the Irish Sea, which is affected by the Sellafield emissions, and some peat bog in Germany, which only received the deposition from global fallout. And you see that the ratio differs really by 1 order of magnitude. And this difference, or I would call it now signature for here nuclear power plant, nuclear power production, and here from the nuclear weapons testing, was now already applied to some studies in the Baltic Sea, which were initiated by our colleagues of the Denmark Technical University, and the samples were measured at VERA. And the first study I want to show you here is on uranium-236, which was found in the Baltic Sea, and the source identification where this would come from. And we would actually expected 2 major sources or major inputs. So a high salinity input from the reprocessing plants here through the Danish Straits, and some input from river runoff. That means just global fallout, which was deposited somewhere at the land and then transported via the rivers into the Baltic Sea. And of course, since this is, we would expect low salinities for this. And this means that we have also low uranium-238 concentrations. Yeah, but when we looked now at the ratios of uranium-233 to uranium-236, we could just use some simple linear mixing model for these 2 inputs to the Baltic Sea, which is represented in this plot by this blue line. Actually, when assuming that we only have these 2 emission sources present, or input sources to the Baltic Sea, we see that all the data from the Danish Strait, they group nicely around that line, whereas the major part of all the data collected in the central Baltic Sea, they are found below that line, so they cannot explain by just the 2 emission sources. And now calculating back, this would mean that we found a surplus of like 200 grams of uranium-236, which was released by some kind of unknown reactor source into the Baltic Sea. And this was published quite prominently in Nature Communications. And of course, we were discussing quite a lot what could be the reason for the surplus. And now in the meantime, our colleagues at the Denmark Technical University, so DTU, they did a number of numerical simulations to find out about the sinks and sources in the Baltic Sea, what you can see here. So they really gotten like precise, some defined numbers out of it. And since they could exclude some remobilization from the sediment in the Baltic Sea, they found that actually these numbers can be explained if you assume that there's some very old uranium-236 from reprocessing still, which was released in the early 90s, still present in the Baltic Sea nowadays. And this, of course, is an important information about about the water exchange of the Baltic Sea, which obviously is very, very slow. I mean, this was known before, but that is like 30 years. This is an important information because it means that all the pollutants emitted into the Baltic Sea, they will also concentrate there. Also, we did analyze some sediment cores from the Baltic Sea, which were collected at these positions, and they were dated. Without going into detail, I directly go to the results of this Landsort deep sediment core, because this gives very interesting results on the emission sources. And I know that this plot is a little bit crowded, but let me guide you through that. Actually, what you see here is again the emission, the explosive yield of the nuclear weapons testing, and the peak in the 1963, and which is directly compared to the depth profile of the results of uranium-236 in black, uranium-233 in blue, cesium in brown, and then the new uranium-233 to uranium-236 in green. And I would like to draw your attention to this very strong peak here right at the beginning of uranium-233 and also uranium-233 to uranium-236, where we find the highest ratios, which are even higher what we had found before. And there we had the discussion with our colleagues that it might be some additional contribution from a device which was tested by the Soviet Union, which had a core where you also had, they used uranium-233. And in addition, we see that whereas we have, of course, some peaks also for uranium-236 and cesium at the time of the Chernobyl accident, we see that we have a dip in this ratio of uranium-233 to uranium-236 as expected from our previous publication. And this means that actually uranium-233 to uranium-236 is really highly selective for the emission of nuclear weapons fallout and marks directly the onset of nuclear weapons testing, which is discussed as the basis of the new geological age or the epoch of the Anthropocene. And this brings me to this application when we were looking for markers of the Anthropocene, also here in Vienna. So we got samples from our collaboration partner, Michael Backreich. They collected samples at the construction site of the Vienna Museum at the Karlsplatz here. We got samples of around only 10 grams and analyzed now the different signals of the long-lived actinides I have already discussed before. And we got actually 4 samples which corresponds to different layers. And the nice information we have now is that the Vienna Museum was opened in 1959, which corresponds quite well with the maximum deposition of global fallout. And you see that you will see a difference in the layer structure at that time. So we are pretty sure about this year, yeah. But of course, it's not like that you really have a good stratigraphy. So you have, of course, you have a very heterogeneous environment, and it was not so clear from the beginning that we would really find the signals here in this very complex area. But we did. So if we compare now our results of the concentrations for the different isotopes of plutonium, neptunium, americium, then you see that at the lowest layer, which corresponds somewhat to the beginning of the 20th century, we have no signal, but then it increases for all the higher or younger layers, which indicates the signal from the nuclear weapons testing. And of course, we also looked now at this new signature of uranium-233. And again, we also see an increase with the younger ages, but most interestingly, you see that the uranium-233 curve flattens, which then means that in contrast to all the other results of the radionuclides, we see that the uranium-233 to uranium-236 ratio is actually decreasing now for younger ages, and which again marks really the basis of the Anthropocene if it is decided that the Anthropocene is to be started or will start, or yeah, that the start of the Anthropocene actually will be defined in the 1950s. And we also confirmed it in a second reservoir at Lake Hallstatt sediments, and we also see the same behavior, which shows you that this is really reproducible result for our new indicator or marker of uranium-233 to uranium-236. I would like to end my presentation with this short outlook, and I really keep it short that we will have some fine time for the discussion. So what are we doing actually now? What are the work we are, or the research and the work we are focusing at the Vienna Environmental Research Accelerator to improve this detection method? Yeah, well, something I have shown you right in the beginning is looking for another isotopes. Especially here, I have shown you the emission, the simulated emission of cesium isotopes after the Fukushima accident. And actually, of course, here now the people were first focusing on the short-lived cesium-137, which would represent an immediate concern, radiological concern, but of course for tracing, it has a rather short half-life of only 30 years. And so for us, more interesting would be the cesium-135, which has a half-life of 10 million years. And of course, we also have to take care about it with this long half-life. And especially interesting, this ratio is because we also, again, we have a certain source sensitivity of this ratio. You see that the ratio from the nuclear weapons testing is around 1, whereas from the nuclear accidents or the reactor accidents is much lower. So we could somehow distinguish cesium emissions from nuclear weapons testing and from the newer input from Fukushima and Chernobyl. And secondly, as I told you before, also I'm interested to develop detection methods for analysis of the very low concentrations of the fission product technetium-99 to get an idea about the general environmental level of technetium just due to the nuclear weapons testing, but because at the moment we just don't know, to get an idea whether the emissions from nuclear medicine are getting relevant in the near future, and if so, what we should do about it to reduce the emissions, because technetium-99, or let's say a certain state of technetium-99, which is short-lived, is used in medicine very, very intensively. So it's actually a most widely used tracer for cancer diagnostics, but in contrast to most other nuclear medical tracers, it does not decay to something stable. It does decay to this very long-lived ground state, which also has a half-life of 10 to the 5 years. And I think that is really important that we get some knowledge about the distribution and the behavior in the environment. The problem now we are facing is that cesium and also technetium, they are very difficult to analyze by mass spectrometry and also by AMS in that case, because it has the same mass as a stable isotope, which is occurring naturally, which will be orders of magnitude more abundant in nature than the radionuclide. So that means we need some new method, and this is the extension of our setup at VERA, which I've shown you before, and it uses the technique of ion laser interaction mass spectrometry. With going into too much detail, you see that it's just a new setup where we have a laser to interact with our ion beam when it's cooled down. And this is to remove these so-called isobars. That means the nuclides, the stable nuclides with the same mass. And that means that this Iliam's method is some kind of an alternative to what actually large AMS facilities are doing, where they have the isobar separation just to the high particle energies they can provide by their accelerators. But what we do here is that we decelerate our ions directly after first mass separation stage. And then, as I said before, we will have an overlap with a laser, which will interact with these now very slow ions, so that we have some time that physical interaction can take place, which might neutralize our ions from the ion source. And also we might have some chemical transformation taking place with the gas filled into this so-called ion cooler, where these particles are slowed down. And actually in that technique, VERA is really the first one where this setup was coupled successfully to an existing AMS setup, and which is already functional and working, and also for some isotopes already in some routine operation mode. Yeah, and this just finally shows what are the isotopes we want to make accessible by mass spectrometry or AMS with this new ILIAMS technique, which are actually shown here either in yellow or in blue. And the green ones are those which we are already able to analyze at VERA right at the moment. And also now strontium-90 already is routinely now analyzed with the new method at VERA. And as I told you before, we are working on the cesium and technetium and also hafnium, and we're doing really some great progress here because we could already suppress sufficiently these stable nuclides with the same mass, so the so-called isotopes, for several orders of magnitude. So that is where our research is going. And with that, I actually already want just to give you some conclusions and short summary that I want you to have in mind that we are now analyzing these radionuclide concentrations really with the most sensitive detection method in the world. That means that fortunately these concentrations are still very, very low, but we have to take care that they stay that low. And of course, therefore we have to understand how they are migrating, how they are distributed, and we have to find out about these emission sources, and there the isotopic ratios helps us, and especially the uranium-233, the uranium-236. There is an important marker for the onset of the nuclear weapons testing, and so it is really source selective as an environmental tracer, which can be used to trace ocean currents. We have found these signals also in the Vienna underground, so that makes them very promising candidates as a marker, the so-called golden spike for the new geological age of the Anthropocene. And just very briefly, I introduced this ILIAMS method to you, which is really a unique method we have here in Vienna at VERA, and which was definitely increase the number of potential new radionuclide tracers which we will have available in the future. Okay, so with that, I'm at the end, and I thank for your attention.